Hi guys, so welcome back. So finally it's the last video for chapter 7. I'm more excited than everyone else. Okay, so in this video I'm going to talk about solubility. So this solubility is related to salts that you already learned back in your high school. I think it's in form 5 if I'm not mistaken. Okay, so what are we going to talk about solubility? So you're going to learn on how to write down KSP expression. So K is another equilibrium constant, but this one is for solubility product. Okay, and then you're going to learn how to calculate KSP values from the given molar solubility or solubility value. Okay, and then you're going to predict, okay, from the calculations, you're going to predict either precipitate will form or does not, okay, by comparing QSP, okay, reaction quotient for solubility product with KSP, okay, and then we're going to learn on the effect of common ions towards reducing the solubility of a salt in a solution. Alright, okay, so let's first learn how to write down the KSP expression. I have here 3 different types of salts, which is calcium chromate, silver carbonate, and barium phosphate. As you can see, okay, the dilution of these salts are reversible reaction. That means, okay, we have a mixture of precipitate with its dissolved solutions, okay, which lies at equilibrium. So we have equal amount of, if it's in equilibrium, we will have equal amounts of precipitate with its diluted or dissolved solution. Okay, so like any other equilibrium constant, okay, that you already learned before, okay, so any pure solid will be omitted or will be discarded from the expression, because we believe that the concentrations of your pure liquid or pure solid are constant throughout the time, and the concentration is constant, is unchanged, so therefore we will not include it in our K expression. Okay, so let's first write down the KSP expression for my calcium chromate. Okay, before you writing down the KSP expression for every salts given to you, you need to make sure the reversible reaction is already balanced. Okay, so in this example, so my KSP is equals to concentration of my Ca2 plus multiplied by concentration of my chromate ion. Alright, and let's look for silver carbonate. Okay, as you can see, the chemical equation is already balanced, so I can just focusing on writing down my KSP. Okay, so number 2 in front of my Ag will be used as the power here. Okay, and then CO3 to minus. Okay, please make sure this one is concentration, so use a square bracket, okay, in your KSP expression. Okay, so this one is my barium phosphate, okay, which consists of 3 moles of Ba2 plus ion. So barium ion to the power of 3, okay, because we have 3 here in front of Ba2 plus, which is its stoichiometric coefficient. And okay, so according to the molecular formula of my barium phosphate, I have 2 for my phosphate ion, but in this reversible reaction there is no 2, so that means I need to put 2 in front of my phosphate ion. Okay, so in my KSP, so to the power of 2. Okay, so this is the KSP expression. Okay, so as you can see, it just involves the aqueous solutions or the ion on the right side, and all the solids from the salts is being discarded from the KSP expression. Okay, so let's learn how to calculate a solubility product from the given concentrations of the ion that is available. Before we proceed with the calculation, you always need to writing down first the equation, okay, for the dissolving the salts into its responding ions. Okay, so for this one, Ca3, okay, so PO4 to solid, okay, reversible reaction, you're going to produce 3 moles of Ca2 plus in aqueous state plus 2 moles of PO4 with the power of -3, okay, in aqueous state. So okay, so my KSP is equals to Ca2 plus to the power of 3, okay, with PO4 3 minus to the power of 2. Okay, so they give you the concentrations of Ca2 plus and phosphate ions are equal, which is 2.9 times 10 to the power of negative 7. Okay, so that means you can just simply substitute the value of the concentration into our KSP expression. Okay, so 2.9 times 10 to the power of negative 7 to the power of 3. Okay, 2.9 times 10 to the power of negative 7 to the power of 2. Okay, so in this one, we can simply simplify because this is multiplication process. So 3 indices for 3 and 2 is multiplied. That means it's going to sum up. Okay, so the base is similar, which is 2.9 times to the power of negative 7. Okay, but the indices here can be add up. 3 plus 2, which is equals to 5. Okay, so it's 2.9 times 10 to the power of negative 7 to the power of 5. So this is just a little bit of mathematics process. Okay, so you need to understand your indices very well. Okay, so if you press your calculator, you will get your KSV value to be 2.05 times 10 to the power of negative 33. Okay, just like any other equilibrium constant value, it does not have unit. Okay, for your syllabus, it does not have unit, even though in reality, it's actually have unit. Okay, so this is your solubility product for calcium phosphate based on the given concentrations of calcium ion and phosphate ion. Okay, so let's look at the second example. Okay, so you were asked, okay, to calculate the concentrations of calcium ion, okay, from the given KSP value and phosphate ion concentration. Okay, so let's rewrite our KSP expression. Okay, is this similar salts from the previous example, so I can just omit or I can just focusing on my KSP instead of writing down the reversible reaction again. Okay, because it's just a similar example as my example 1. Okay, so Ca2 plus to the power of 3 because 3 here, and then PO4 3 negative to the power of 2. Okay, my KSP product is 2.05 times 10 to the power of negative 33. Okay, the concentration of Ca2 plus, okay, to be found through the calculation. And for my phosphate ion is given there 0.010 molar. Okay, and then a little bit of rearrangement, okay, for you to calculate your calcium ion. Okay, so it's 2.05 times 10 to the power of negative 33. Okay, this concentration of phosphate ion, if we transfer it into the left, that means it's going to be divided 0.010 to the power of 2. Okay, so we have here calcium ion concentrations to the power of 3, and if we want to know what is the calcium ion on itself, so we have to be square root of 3. Okay, so this is concentration. That means it has unit of molar, mole per liter. Okay, so the answer is 2.74 times 10 to the power of negative 10 molar. M, big M. Okay, so what about this one? Okay, so you're given a molar solubility. Molar solubility sometimes being written down as small s. Okay, so molar solubility is just simply the molarity, okay, for that salts. Okay, so when it dissolves to form ion, so these salts will have this solubility value in its molarity value. Okay, so if you want to calculate KSP value from the given molar solubility, you need to fill up a simple ice table which include initial changes and equilibrium concentration. Okay, so let's start. Okay, so S. Okay, molar solubility, I will denote it as S. Okay, so my barium sulfate initial concentration is definitely 0. Okay, we can just ignore this barium sulfate because it's a solid. Okay, so it will not alter anything in your equilibrium reaction. Okay, so barium 2 plus. Okay, so barium sulfate, okay, If you write down the reversible reaction, you will produce 1 mole of barium 2 plus ion plus SO4 2 negative ion and 1 mole 2. So therefore, since it's 1 mole of barium ion, so this one is just plus S, okay? So instead of using X for changes like any other examples of your ice table in chapter 6 and chapter 7, okay, which is on other part of your chapter 7, but for solubility product, okay, so we're going to use changes in the terms of S, okay. So it's just simply the same technique as the same concept like your X, okay. If it's 1 mole of the compound, so it's 1S. If it's 2 mole, then 2S, or something like that. It's just similar. But instead of using X, we are changing it with S, okay. So for my sulfate, it's positive S again, okay. So equilibrium is just simply initial plus changes, okay. So plus S and plus S, okay. So KSP is equals to Ba2 plus SO4 2 negative, okay, which is in the terms of S times S, so equals to S squared. And our S here is 1.05 times 10 to the power of negative 5. So we substitute the value of S into the expression. Okay, so you will get your KSP value to be 1.103 times 10 to the power of negative 10. Again, strictly no unit. Okay, so let's look at example 4. Okay, so they give you another molar solubility, but this time is for silver bromide. Okay, so write down first the equation for the dissolving silver bromide salts in water. Alright, so solid or silver bromide solid can be ignored. We can just put dash on it because it's a solid. Okay, so this one, molar solubility is for S, okay. So 0 initial concentration plus S for silver ion and plus S for bromide ion, because it just have 1 mole of silver ion and 1 mole of bromide ion produced from the dissolution process. Okay, so this is plus S and plus S. Okay, so write down the KSP expression again. Okay, which is Ag plus and then Br negative. Okay, substitute the concentration in the terms of S. So S times with S, which is equals to S squared. Okay, so they give you already the molar solubility. So you can substitute the value of S into the expression. Okay, to the power of 2. And you will get your KSP value to be 5.041 times 10 to the power of negative 13. Okay, so how was it? Do you have a good understanding on how to calculate solubility product from the given molar solubility? So how was it? It's easy, isn't it? Okay, so I have shown you 2 examples. And the first one, if you are given the concentration, so in the terms of concentration, you can just simply substitute the value of the concentration into your KSP expression. And this is the second one, when you are given the molar solubility, and we're going to use the term S in the ice table, and you're going to substitute the value of the molar solubility into the KSP expression and to calculate the solubility product. Let's move on the next example, okay, which is instead of giving you the molar solubility, okay, this time they give you solubility. So molar solubility in the terms of mole per liter, in the unit of molarity, which is mole per liter. But if its solubility is in the unit of gram per liter. Okay, so for this one, if you are given a solubility, you need to convert your solubility into molar solubility by how? Okay, so molar solubility is just simply solubility, okay, the given solubility, you divide with the molar mass. Okay, so the solubility given here is 0.67 gram per liter, and the molar mass given here is 136.2 gram per mole. Okay, so you will get your answer in mole per liter which is 4.92 times 10 to the power of negative 3 mole per liter, or simply can be substituted as big M. Okay, so when you have the molar solubility, now you can substitute into your ice table. Okay, but before we proceed by filling up the ice table, again I emphasize to you, please write down the dissolving equation so that you can know how many moles of ion is actually present. Okay, according to the stoichiometry coefficient, so you won't get any mistakes on your KSP expression calculation. Okay, so dash 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 for calcium sulfate. Okay, so my calcium ion is 1 mole and sulfate ion is 1 mole. Okay, so initial 0 and then plus S for both ion, and therefore equilibrium is just the same. Okay, so my KSP is calcium ion, okay, and then sulfate ion. Okay, in the terms of S times S, which is equal to S squared. Okay, so my S, okay, I already calculate it, okay, which is 4.92 times 10 to the power of negative 3 molar and to the power of 2. Okay, so therefore, okay, so you will get your KSP solubility product to be 2.42 times 10 to the power of negative 5. Again, no unit. Okay, so let's try with a different example, which is this one, example 6. Okay, so we done with calculating solubility product, but now let's manipulate the value of solubility product to determine what is the molar solubility or solubility of salts. Okay, so magnesium hydroxide, if you write down the solution, the dissolving okay, so for this one, if you write down the equation, okay, so it's 1 mole of magnesium ion and 2 mole of hydroxide ion. Okay, so they give you the KSP value. Okay, so we have to sketch the ice table first. Okay, so Mg, which is in our ice table, okay, so initial concentration in molar dash for magnesium hydroxide, 0 for both the ion. Okay, so changes is in the terms of X. So 1 mole of Mg2 plus, that means plus S, but 2 mole for my hydroxide ion, that means it's 2S. Okay, and then equilibrium plus S and 2S as well. Okay, so I'm going to write down my KSP expression, which is consisting of Mg2 plus concentration multiplied by hydroxide ion concentration to the power of 2, because we have 2 in front of the hydroxide ion. So I'm going to substitute my KSP value in the terms of S. Okay, so magnesium ion, it is S, whereas for my hydroxide ion is 2S and is to the power of 2. Then I simplify it, it becomes, okay, 2 to the power of 2 is 4, and S to the power of 2 is S2. So in total, I have 4S to the power of 3, which is equivalent to my solubility product value. Okay, so if I want to calculate my S, so that means I'm going to divide my KSP value with 4, and then the answer is being square root 3. So my S that I calculate is 1.55 times 10 to the power of negative 4, and molar solubility is in molar. Okay, the unit is M, big M. Okay, so how do I convert this molar solubility to solubility? Okay, so solubility is just simply number molar mass is multiplied by the molar solubility. Okay, so the molar mass of my magnesium hydroxide is 58 gram per mole. Okay, and my molar solubility is 1.55 times 10 to the power of negative 4 mole per liter. Okay, so the solubility is equivalent to 8.99 times 10 to the power of negative 3 gram per liter. If we want to find out either precipitate can form or not from our given solids or salts, okay, so we're going to calculate what is the QSP value. So QSP is the reaction constant for solubility product, and we're going to compare it with the value of KSP stated in the question. Okay, so there are three possible cases. Either QSP is less than KSP, or is equal or is greater than the KSP value. If it's less than KSP, so that means we are having unsaturated solution, so no precipitation can occur. But if the QSP is equal to our KSP, that means the system is at equilibrium, so it has a saturated solution, equal rate of precipitation formed with the rate of the solid being dissolved. Okay, and if we have our QSP to be greater than KSP, we are having a supersaturated solution, which definitely precipitate will form until our QSP equals to KSP. Okay, so let's try now to find out either a precipitate will form or not based on the mixing these two different solutions. Okay, so we are going to mix potassium sulfate with lead nitrate. Okay, and we are going to form from the reaction, we're going to form lead sulfate. Okay, so lead comes from the lead nitrate, which is PbNO3, okay, to the power of 2, whereas my sulfate ion will comes from my potassium sulfate, K2SO4. Okay, to find out either a precipitate will form or not, we need to calculate what is the QSV for the formation of lead sulfate salts. Okay, but you only have the concentrations of potassium sulfate and concentrations of lead nitrate. Okay, your concentration of your sulfate ion comes from the concentration of potassium sulfate, which is 0.010 molar, whereas the concentrations of your lead come from your lead nitrate, which is 0.10 molar. Okay, so let's first write down the formation of my lead sulfate, which is PbSO4 solid. Okay, reversible reaction, so you're going to produce 1 mole of lead ion plus sulfate ion equals, okay, so my KSP expression, okay, but since we are going to calculate reaction quotient, so we use QSP, okay, equals to concentrations of my Pg2 plus with SO4 2 negative. Okay, so we're going to substitute the concentration into the expression, which is my lead to be 0.10 and for my sulfate is 0.010. Okay, so you get your QSP value to be 1 times 10 to the power of negative 3. Okay, so the KSP value for the formation of lead sulfate is 1.8 times 10 to the power of negative 8. Okay, whereas the QSP that we calculate just now is 1 times 10 to the power of negative 3. So if we compare, we definitely have QSP greater than KSP. That means we are having a supersaturated solution. Okay, so that means supersaturated solution is going to have precipitate, and so precipitate will form until QSP equals to KSP. Okay, so let's look for another example. Okay, so now instead of giving you concentration, they give you the volume. Okay, so that means there will be a change in the number of mole and as well as in the change of the concentration before and after mixing. Okay, so I'm going to mix sodium sulfate, 200 milliliters of my sodium sulfate with this concentration with 600 milliliters of lead nitrate. Okay, so from the reaction, I'm going to produce lead sulfate. Okay, so let's first calculate the number of moles of lead ion and sulfate ion that is present initially from the given concentration and volume of our two different solutions. Okay, so lead ions come from my lead nitrate, PbNO3, whereas my sulfate ion comes from my sodium sulfate. Okay, so you have to calculate the number of mole. Okay, so let's do for sodium sulfate first, which will give you the number of mole of my sulfate ion. Okay, so how to calculate number of mole is just simply volume in liters, okay, multiply by the molarity, okay, which will give you 8 times 10 to the power negative 4 mole. Okay, whereas for my sulfate ion, for my lead ion, okay, which comes from my lead nitrate, so I have 600 milliliter, which we convert into liter, and the concentrations of my lead nitrate is 0.008 molar. So that means our number of mole is 4.8 times 10 to the power negative 3 mole. Okay, so the new volume after mixing is 200 milliliters plus with 600 milliliters, which is equals to 800 milliliters. So that means you need to calculate the new concentrations of lead ion and your sulfate ion after mixings by dividing the number of moles of the sulfate and lead ion with the new volume. So our final volume is 800 milliliters. If we convert it into liters, it's equal to 0.8 liters. So let's first calculate the concentration of my lead ion. Okay, so the number of moles of my lead ion is 4.8 times 10 to the power of negative 3 mole. Okay, divided by the volume, final volume, which is 0.8 liters. So I will get it to be 6 times 10 to the power negative 3 molar. Whereas for my sulfate ion, the new concentration should be 8 times 10 to the power of negative 4 mole divided by 0.8 liters. So you will get 1 times 10 to the power of negative 3 molar. Okay, so this is the new concentrations of both lead ion and sulfate ion. Okay, so we're going to find out either this mixture going to form lead sulfate precipitate or not. So we're going to calculate what is the QSP value. Okay, so QSP for this one is just simply write down first the expression, which consists of lead ion concentration multiplied by sulfate ion concentration. Okay, so from the dissolution of my lead sulfate salts, okay, reversible reaction. Alright, so my lead ion concentration, the new concentration that we calculate before is 6 times 10 to the power negative 3. And for my sulfate ion is 1 times 10 to the power of negative 3 molar. So we will get our QSP to be 6 times 10 to the power of negative 6, which is larger than the KSP value stated, which is 1.8 times 10 to the power of negative 8. So my QSP is greater than KSP. That means again we are having a supersaturated solution. Okay, so precipitate will form until QSP equals to KSP. Okay. Okay, let's move on to the next example. Okay, which after we learn about common ion effect. Okay, so common ion has been introduced to you in your buffer solution. Okay, so in this one, okay, if we are having common ions between our solvent and the salts that we're going to dissolve, it will reduce the solubility. We are dissolving silver bromide in pure water versus in the sodium bromide. So in the pure water, we don't have any common ion for silver ion or bromide ion. So the solubility is just from the molar solubility of your silver bromide. But once we are dissolving my silver bromide sodium bromide solvent, okay, so there are common ions present between these salts and the solvent, which is bromide ion. So the presence of the bromide ion will affect the solubility of this silver bromide, and it's believable and it's going to be proved that silver bromide has higher solubility in pure water compared to in the sodium bromide solvent. Okay, So let's look with the example 9 for you to understand the effect of common ion towards solubility of silver bromide. So first, let's recalculate what is the solubility of your silver bromide in the pure water. Okay, so we start with silver bromide in pure water with 9 concentration because it's a pure water. So we're going to fill up this ice table, but before that, we have to first write down the reversible reaction or reversible equation. Okay, for the dissolving reaction. Okay, okay, so solid 9. Okay, so my silver ion, it starts from 0 initial concentration plus S and plus S for both of the ion because it's just 1 mole, and equilibrium is just simply initial plus changes, which is plus S and plus S. So my KSP equals to Ag plus and then Br negative. So change it in the terms of S. I have S squared and my KSP is 7.7 times 10 to the power of negative 13. So if I calculate my molar solubility by square root of the KSP, okay, I will get my molar solubility to be 8.77 times 10 to the power of negative 7 molar. So this is the solubility or molar solubility of the silver bromide in pure water. Okay, so let's look when we dissolve our silver bromide in sodium bromide. Okay, so now we are dissolving our silver bromide in 0.001 molar of sodium bromide, and the common ion here is bromide ion. That means our bromide ion will have initial concentration of 0.001. Okay, 0 for my silver. Okay, and changes is in the terms of S, so both are having S. Okay, but equilibrium for silver ion is plus S, whereas for my bromide ion is 0.001 plus S. Okay, so if we write down the KSP, okay, so now we have S multiplied by 0.001 plus S. Okay, so this one we can make an assumption by considering that S is very small. So assume S is very small. Okay, therefore 0.001 plus S is equivalent to 0.001. Okay, so simplify our KSP. I will get it to be S times with 0.001. So my KSP is 7.7 times 10 to the power of negative 13. So if I want to get my S value, I can just simply divide my KSP value with 0.001 to get my S, where my S is to be found to be 7.7 times 10 to the power of negative 10. Okay, so in the pure water, my S value is 8.77 times 10 to the power of negative 7, whereas in 0.001 NABR, okay, my S is 7.7 times 10 to the power of negative 15 molar. So, my molar solubility is smaller when I dissolve my silver bromide in the sodium bromide solvent. Okay, so that means the solubility is smaller, okay, when we have common ion present between the salts and the solvent. Okay, so solubility is lower in NABR because of the common ion Br negative that is present. Which reduce AgBr silver bromide solubility. Okay, alright. So let's look for another example. Okay, so now you were asked to compare the solubility of lead sulfate in pure water and when it is in 0.01 molar of lead ion solution. Okay, so you were given the solubility. That means you need to convert first the solubility into molar solubility. Okay, so that you can calculate what is the KSP value, because in the question they don't give you what is KSP value. Okay, before you can compare the solubility, you need to first find out what is the KSP value. Okay, so first we need to convert this solubility into molar solubility. So molar solubility is just simply solubility divided by molar mass. Okay, divided by molar mass. So my solubility is 0.038 gram per liter, and the molar mass for my lead sulfate is 303.3 gram per mole. Okay, which I get my molar solubility to be 1.253 times 10 to the power of -4 molar. Okay, so then let's write down the lead sulfate equation. Salts and we're going to write down what is the KSP expression for my lead sulfate, which consisting of just lead ion. Okay, so we're going to substitute the value of molar solubility here into the equation. So the KSP value for my lead sulfate at this set of temperature is actually equals to 1.57 times 10 to the power of -8. So we're going to use this KSP value calculated to determine what is the solubility of my lead sulfate in water and as well as in lead ion solution. Okay, so let's, if it's in the pure water, okay, so the molar solubility is just simply like what we already calculated before from the solubility, which is 1.253 times 10 to the power of -4 molar, which we use to calculate KSP value. But if we have the lead sulfate dissolved in lead ion with initial concentration of 0.01, okay, so it becomes plus S, 0.01 plus S, and plus S. Okay, so we're going to assume S is very small. So therefore 0.01 plus S is equal to 0.01. Okay, so let's substitute into our KSP value. So KSP equals to Pb2 plus SO4 2 negative, okay, which is equals to the calculated KSP from the previous slide, which is 1.57 times 10 to the power of -8. Okay, so we substitute with 0.01 for my lead ion, time with S for my sulfate ion to get 1.757 times 10 to the power of -8. And my new molar solubility in this lead ion solvent is 1.57 times 10 to the power of -6. Okay, so this is my solubility in pure water. Okay, and the new solubility in ion and my new solubility in a solvent containing lead ion is 1.57 times 10 to the power of -6. Okay, so this is in the Pb2 plus solvent. Okay, so as you can see, the value of molar solubility is smaller when I dissolve my lead sulfate in the solvent containing lead ion. Okay, so lower solubility in the Pb2 plus solvent because of the presence of common ion. In Pb2 plus, leading the lead sulfate to less soluble in the solvent. Okay, so the presence of common ion between the solvent and the salts will reduce its solubility. Okay, so I'm done explaining to you about anything that you need to know about solubility. So we already learned on how to write down our solubility product expression, KSP, okay? And then we already learned on how to calculate our KSP value from the given molar solubility as well as in the solubility. Okay, so we also already learned on how to calculate our molar solubility by using ice table, okay? And then we also learn on how to identify or predict either a precipitate will form or not when we mix two different solutions together, and we're going to compare between QSP and KSP. Okay, so let's move on with the final task of your chapter 7, which is quiz 8. So there are 3 different questions. Okay, so I hope you can try to answer these questions, and please submit to me in our Google Classroom again after we discuss about it during our week 18 tutorials. Okay, so bye. Thank you for watching, guys. See you guys again in my next tutorial. Bye bye.